Hello students, and welcome to Domain and Range of Functions measurement topic. One of the learning targets has to deal with being able to write intervals of numbers using interval notation or set builder notation, which we're just going to call set notation. But before we do that and get into it, we need to review classifications of different types of numbers. So let's do that right now. We have various types of ways to classify numbers, and we're going to start off with the basic ones. One way is to identify numbers by, are they natural numbers? And one way we denote that is we use a capital letter N to denote natural numbers. Now, natural numbers are also known as counting numbers, and basically, as counting numbers describe, how many items can you have? You can have one book, two books, three books, four books, etc., etc., etc. Keep on going on. So those are natural numbers. Whole numbers. Whole numbers, we use a capital letter W to denote whole numbers, and whole numbers are natural numbers plus zero. So whole numbers are 0, 1, 2, 3, 4, etc., going on forever. Integers. Integers are positive and negative whole numbers. And we use a capital letter Z, not I, but Z to denote integers. And like I said, those are positive and negative whole numbers. So what we're looking at are numbers like, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. And with each value greater than, each whole value greater than 3, and each opposite or negative whole value less than 4. Rational numbers. Rational numbers are denoted with the capital letter Q, and rational numbers are any number that can be written as a fraction of two integers. So rational numbers are ratios or fractions of two integers. Now, when you write a rational number as a decimal, they'll always have one of two conditions. As a decimal, the decimal number either repeats or terminates. So examples of that, let's say 3 over 4. An integer over an integer is a decimal, that's 0.75 and ends, terminates. Or if we have 1/3, that is 0.3 repeating, 0.3333 going on forever. So those are two different examples of rational numbers. Irrational numbers. Irrational numbers, as the name implies, are numbers that aren't rational, and we use a capital letter I to denote irrational numbers. And basically, when you rewrite irrational numbers as decimals, they're going to be decimal numbers that do not terminate nor have a repeating pattern. Examples of that are the number pi, which is approximately 3.14, but it's 3.1415 ... goes on forever, doesn't repeat. Or something like square root of 2. If you put square root of 2 in the calculator, you get 1.41. That decimal number keeps on going on. It stops on the calculator because the calculator cannot go on forever. But if you keep on working it out, that decimal number goes on forever and doesn't repeat. So those are irrational numbers. And then finally, all those numbers put together, irrational numbers and rational numbers, make up real numbers. And we use a capital R for real numbers. And basically, real numbers are all rational and irrational numbers. They are not imaginary numbers, which you'll learn about later on this year. Nor infinity. Infinity is more of a concept, means it goes on forever. But basically, all the numbers that you've been dealing with your whole life are real numbers. Since we're talking about set notation and interval notation, it's good to have a better understanding of what a number set actually is. So, a set is a collection of items called elements. A set can be finite, which means it has countable numbers of elements. Example. The outcomes of a roll of a die. So that means when you roll die, you could roll a 1, or you could have 2 dots, or 3 dots, or 4 dots, or 5 dots, or 6 dots, but that's it. So you got 6 finite different outcomes. The other type of set can be one where you have an infinite number of outcomes. That means you have unlimited number of elements. An example of that will be all real numbers between 1 and 5. Because I could pick number 1. I could pick the number 1.1. I could pick the number 1.11. I could pick the number 1.111. I could pick the number 1.1111. I think you get the figure and the idea. But there's an infinite number of numbers that I could write down between 1 and 5. So that's an infinite number set. So now that we learned a little bit about number sets, how are the different ways that number sets can be described? There are 4 different ways that mathematicians usually describe number sets. The first way is just words. That is a literal verbal description of the number set. So an example, the set of all real numbers less than 3. Or the set of all even numbers between 2 and 10. That's it. Just actually literally using words. The other way we can do it is called using a roster notation. So what we do is we use, let's say for this example right here, the set of all even numbers between 2 and 10. We would actually use braces to break down all even numbers between 2 and 10. So 2, comma 4, comma 6, comma 8, comma 10. And down up here, I'm going to put the word inclusive, meaning that we are including 2 and 10 in our set. So that's roster notation. Roster notation, it can be used for both finite and infinite number sets. The last two are interval notations and set notation. I'm going to call it set builder notation, but the verb terminology we're going to use as we move on is set notation. Depending on what resource you're looking at, you might see it called as set notation. Other resources might call it set builder notation, but for our purposes, they're one and the same. Let's go into interval notation. Now, interval notation is the set of all numbers between 2 endpoints. Interval notation always represents an infinite set and we use 2 different types of symbols to denote if we include an endpoint or if we exclude the endpoint. So we use parentheses. We use a parentheses symbol when we exclude the endpoint. And we use that curve symbol there, the square curve symbol, when we include the endpoint. And what I mean by that is when we include it within the set of all numbers between the two endpoints. So now what we're going to do is we're going to practice a little bit with this notation. Before we get into the examples A through D, I just want to highlight this information down here. Once again, we use the square symbols, which means that we include the endpoints. We use parentheses when we exclude the endpoints. And we could use a combination if one of the endpoints is included and one of the endpoints is not included. So looking at example A, endpoints are 1 and 4, negative 1 and 4, and we know we include them because these dots here are solid. So solid dots, we include those endpoints. So the way I'm going to do this is I'm going to start, and we always go from left to right. So my interval between negative 1 and 4, I would write that down as negative 1, comma, 4, and I'm going to use the square brackets there, or braces, to denote that I am including negative 1 and positive 4 in this interval. Now, example number B, or letter B. Once again, same interval, but negative 1 is still solid, means I include it. But since I have an open dot at on the number line at 4, that means I exclude it. So open dot means you exclude the value from your interval. So I'm going to start negative 1, but since I'm including it, I use a square bracket. And I'm going to go all the way from negative 1 here, solid. And I want all the values between that and positive 4. But I don't include positive 4. So I use a parentheses. That means you do not include the 4. So it's everything up to and almost touching 4, but never touches 4. All right, let's look at C. Once again, open dot. My lowest value is 4. So I'm going to use parentheses since I don't include the 4. But all my values on my solution, or that's being graphed, are values that are greater than 4. And it doesn't end. It goes on forever. And if it goes on forever, it means it goes out to infinity and beyond, to quote Buzz Lightyear. And since we can never reach infinity, whatever large number you come up with, I can always add 1 to it. We don't include infinity. Can't be included. So you close it with the parentheses and not a square bracket. And then in D, we have 2 parts on our number line that are being accounted for. We got the part that's less than negative 1, but doesn't include negative 1. We also have the part where we're at 4 on the number line, including 4, because it's a solid dot, and everything greater than that. So we're going to have 2 different interval notations being connected with a union symbol. So let's look at how to write the interval notation for all the numbers less than -1. Well, what value is all the way here going to the left? Every number that's less than -1. Well, that's going to be negative infinity, because we're going to keep on getting smaller, 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 and whatever large negative number you come up with, I can always take one less than that, which will make it even larger. And we're going up to -1. Now, since it's an open dot, I use parentheses. I'm not including it. Now, there's a second part to it. All the values over here that are greater than 4, including 4. So what's in this part of my graph, the smallest value I could have on that part is +4. No, I'm including it, so I'm going to use a square bracket. But then all my numbers going to the right keep on going on forever toward positive infinity. And once again, you never reach positive infinity, so we don't include it. So we use a parentheses. And since I have both these parts in combination, we use a symbol that looks like a big U. And that means union. So I have the left interval in conjunction or in union with the right interval. Set builder notation is the final way we represent a number set. In set builder notation, we usually use inequality symbols. Come on. And we introduce a new notation or new symbol, and that is this fancy E. And that fancy E means an element of. That's a translation of that. That's the element symbol. And it's spelled like very neatly, but element symbol. So what that means is basically we got to learn how to write in mathematical shorthand. So let's say I have all integers greater than -4. So what that really means, I'm looking at, and I'm excluding, I want all right, let's make it 4.5, -4, 4.5. Makes it easier. So my values there, if I did in roster notation, would be -4, -3, -2, -1, dot, 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 going on forever. Well, using set notation, we're going to use, first off, braces, and everything's going to go inside these braces when we do this. But we're going to write it down like this way. We want all values of x that are elements of integers. So we use that fancy E, the element symbol. We use a capital Z to denote integers. So we want all values of x that are integers, elements of such that, and to do such that symbol, we use a vertical line. That means such that. And then we want all the values that are greater than 4.5. So we want all the value integers, which are the x's in this case, since they are all elements of integers. that are greater than negative 4.5. That's just a different way of saying all integers greater than negative 4.5. And that's your first example of set notation. So what we're going to do is we're going to do a few more examples, and hopefully you'll catch on the pattern. So we're going to look at the 4 examples that we did using interval notation and redo them using set notation. So example A, we have all the values between negative 1 and 4, including negative 1 and 4. So we want all the possible values between them. So these will be all real numbers. So the way we're going to write this is, we have a number set where we have all values of x that are real numbers. And to do real numbers, I said capital R earlier, but usually we use it where we have these 2 vertical lines to draw our R. That kind of is a fancy way of showing real numbers, so I'm going to use that. So we got all values of x that are real numbers such that x is going to be greater than or equal to negative 1, and x will be less than or equal to 4. And that's it. So the first condition right here tells us what type of numbers we're dealing with. And then this is the condition on the restriction upon that number set. All right, B. We want all the values between negative 1 and 4, excluding 4 but including negative 1. So once again, since we want all the numbers between those two, and it's continuous, we're talking about all real numbers. So we have a number set where we have x is an element of all real numbers, and such that x is greater than or equal to negative 1, and x is less than 4. That's an and condition when it's between 2 numbers. So negative x is less than negative 1, and x is actually less than or equal to negative 1, and x is messing that all up. X is greater than or equal to negative 1, and x is less than 4. All right, let's get C. In C, we have all the values of x greater than 4, but excluding 4. So we have x is an element of all real numbers such that x is going to be greater than 4. That's it. And then the last one, where we have 2 parts. We have the condition where we have all the values of x less than negative 1, excluding negative 1. Or we have this region over here where x can be greater than or equal to 4. So to do that in set notation, put our brace down, and we got x, which once again are all real numbers. So x are elements of real numbers such that x is going to be less than negative 1, or x can be greater than or equal to 4. And that's it. So in these final 3 examples, what I'm going to ask you to do, well, I'll do the first one with you, and then the next 2, pause the video, work on it, and then check your answer. So the first one, we have all the values of x that are greater than 2. So using interval notation, we do not include 2, so I use parentheses for the left value endpoint of positive 2. And since x goes on forever, that means x is going to head toward infinity. All right, for set builder notation, we have all the real numbers such that the real numbers are going to be greater than 2. And that's it. With example 2, I want you to pause the video, try on your own, and then come back and play the video and see how you did. Do it now. All right, so what's going on here? We have all the values of x that are less than or equal to 2. So with interval notation, our left endpoint is over here at negative infinity. And our right endpoint is over here at 2. And I include it, so I use a square bracket. And using set builder notation, I have all real numbers, so we do that using x as an element of all real numbers, such that x is going to be less than or equal to 2. And that's it. Once again, try this, pause the video, then try it, and then come back and check your answers with the continuation of this video. So please pause and try now. All right, so we got 2 regions that are on the number line that are being focused upon. We have the region between -1 and +1, but not including them. So that'll be -1 comma +1. We use in parentheses. But we have another region. So we use the U, that U symbol for union. That translates to or. And the second region is the region between 3 and 4. But we include 3 and 4, so we use square brackets. And that's how we do that. So for set builder notation, we have all real numbers. So x is an element of all real numbers, such that x is going to be a little greater than -1, but less than +1, or x is going to be greater than or less than 3, but x will be less than or equal to 4. And that's it. So what we need you to do now is to try practicing this, and there will be some problems on your practice that are a little bit different than these, but the concepts will be the same, and your teacher will help you out as you go along, or your competent classmates. All right, take care. Bye-bye.